in differential equations. And to kind of just make some definitions and make sure that we've got a few things that are clear as one starts to dig into certain various spaces. And you might be looking at this for a lot of different reasons. But if you look at what might be a single state variable differential equation, usually this is going to mean I've got one free parameter. And in fact, when we usually start off doing differential equations, this is where we spend a lot of our time in a single state variable case. Meaning I've got one thing that's sort of changing over time, first order derivative, if you want to put it that way, equals then to something that is, in a linear case, maybe some coefficient a. Lots of different things are possible, but this is where you would begin. And there's a number of different questions that come out of this as soon as you begin. First thing is to notice is, what is the steady state? Well, steady state basically says what happens when the derivative, when everything is not changing anymore. Very simple starting definition. Well, if something is not changing, if it's not changing, that means then the derivative equals to 0. So therefore this must be 0. Therefore everything on the right-hand side of this equation must be 0. Well, in this case, that's pretty trivial because that means if this has to be equal to 0, that's a scalar, assuming it's not 0, then it has to be equal to 0. You're like, great. Okay, that makes some sense. And in fact, you could take this differential equation or a different form of it, maybe pull the a on the other side, invert the sign, you get this kind of an equation, which looks much more familiar if you're an electrical engineering structure, or if you're looking at various other engineering structures where you might imagine this is kind of a filter, and in fact kind of almost a either a low-pass filter or sets up a system that looks like it'll start an initial condition and decay to a solution. You'll see this used in many, many, many places. So in this case, what you're going to see is that I'm going to have x of t is going to be equal to its initial condition, and then this is going to be the core of that solution, e to the minus t over tau, where this tau is exactly that variable. And you think, okay, that makes a lot of sense where this is beginning. Now, a couple interesting definitions, right? Because I can now start to say, well, imagine this derivative could actually be that initial term, plus it could be a driving force, maybe it's b of t. Interestingly enough, the steady state is still when this is equal to 0, and I get a particular steady state out. That input could also have its own value. It could be a weighting value, it could be a coefficient, and in fact, I could start getting some interesting ratios of various terms. We'll typically talk about if I have x, and it's not bolded in lowercase, it's a scalar. If I have w and it's lowercase and not bolded, it's a scalar. Interesting enough, if x is in bold, you usually will think of it as a vector. And then if it's also that and a capital quantity, you're usually thinking of it a matrix. Now, if we're going to go to higher order tensors, things will get more complicated, but we'll start here. And this is usually a good way to start thinking about things. So if you talk about a vector of state variables, you can actually get differential equations that involve vectors and matrices. And you think that's really cool, because now I could have dx of t dt equal to this matrix A times x of t. Now, this would have a number of state variables, which is equal to the number of various state variables of the length of the vector of x of t. You're like, cool. And this matrix you would likely expect would be a square matrix because it would go from x vector of t to this derivative of x of t. So that works out really well. And you can actually say, okay, that's an interesting differential equation. Maybe also a scary differential equation, depending on how you look at the world. On the other hand, you could also, again, a simpler form is to say, imagine I have a vector y is dependent on an input vector x times a matrix w. And this is, of course, a characteristic operation called a vector matrix multiplication, because it's a vector times a matrix equals a vector. And so that typically works out very well, very, very useful operation, and gets used almost everywhere. The only problem you look at this is you go, how do I solve this in general? What is an easy way to do this equation? Because this one Suro solved very nicely with a nice exponential. You might go, wow, I really wish there would be like an e to the matrix A times t. That would just make life easy. Well, it turns out there kind of is a way to do this, and there is a mathematical approach to this, and there's a couple different ways to come at this answer. So even in the matrix formulation, there are very sort of straightforward ways to think about this. You don't get everything because like variables don't commute, because that's typically true with the rings that you have that are matrix operations. But there's a lot that you can work with here. And that's something that one might want to kind of look at when you look at any of these differential equations and realize there's a whole bunch of opportunities in any of these systems.